Greetings and welcome, internet friends. Mr. Waddy here. We're doing part 2 of Algebra 2.10.03, two-way tables and probability. And so today we're hitting the third type of relative frequency, which is conditional relative frequency. And that is the ratio of a joint relative frequency, and so I'm going to need to use this piece here, to the marginal relative frequency. And actually, maybe I can, let's do that. So this is so I'm reducing it to a particular row or column, is what my outcome space is, and then the success would be a particular joint relative frequency. And so this relative frequency, which is kind of like a probability, is essentially going to be the ratio of those two things. And the word conditional is showing up, by the way, just like it did with conditional probability. And so that's going to be stuff like the probability of B given event A had already occurred. And so in the case of example 3, it would be, right, the probability that someone is attending given we already knew they were a junior. And so we're reducing the total outcomes to a particular row or column. All right, so here's example 3, and I've got a whole bunch of information already from previous problems copied up here. And so it says, use the survey results in example 1 to make a two-way table that shows the conditional relative frequencies based on the total rows. Okay, and so here the first table is simply the joint frequencies, these 4 cells, and the marginal frequencies. So those are not relative, those are literal quantities, numbers of juniors that responded, for instance. This next table is showing the joint relative frequencies here, in which we did the ratio of the number of juniors to the total number of students that were surveyed. Okay, number of juniors attending in that cell, sorry. And then out on the outside were the marginal relative frequencies, in which we added up those rows or columns to get those outcomes. And now we're going to do the conditional relative frequency, and keyword here is based on the row totals. And so there are actually 2 different ways I could set up this table here. I could have based it out of the columns or the rows, and so we're going to be using the rows. And so since I'm calculating this based on the rows, I'm basically saying, what is the probability someone is attending given that I already know they're a junior, or the probability that someone's not attending given that I already know they're a junior. And so as a result, the denominators for my top row are going to be the 0.482, and the numerators for the top row will be the joint relative frequency for that given cell. And so 0.191, and here it would be 0.291. And so this is answering the question, or I guess like for this cell right here, I'll do an analysis. This would be the probability that someone is attending given they are already a junior. And so it's analyzing a portion of the population. And we've, I think, already alluded to some of that in our analysis in the previous video. All right, but that's kind of what that would be looking at. And then the senior, since we're going by rows, these denominators would be 0.518, 0.518, check. And the numerators would be these decimal values. So 0.35 and 0.168. All right, and so hopefully you're seeing where these are coming from. Since I'm doing this by row, I'm literally, saying, another way I guess I could say it is, I'm doing 0.191 divided by both of those added together, which is what that represented. And so it's still, right, kind of part divided by total successes out of total outcomes, things like that. Still behaves the same way. And so if I evaluate these, I get 0.396. Here I would get 0.604. Here I would get 0.676 and 0.324. And so what these represent now is that this is the probability that someone is attending given I already knew they were a junior. And so you could say 39% of juniors are attending, 60% of juniors are not attending, while 67.6% of seniors are attending and 32% of them are not. And so I don't know, maybe this, I think this was what, like a school concert or something like that, but I don't know, maybe it could even be like prom or something like that. And it's indicating that seniors are more interested in going to this than the juniors were. All right. Let's see. Is this one worth looking at? This is monitoring progress question 3. Use the results in example 1 to make a two-way table that shows based on the column totals. And so this is exactly the same set of data. It's just this time I'm working by column. All right. And so that's the way that we'd be running it. I might not do this whole problem. I might just do the setup. So 0.541, 0.541 would be the denominators. And over here, so this would basically now be, well, okay, this actually might be worth explaining. The more times we allow our brains to experience and be exposed to these ideas, the better we'll understand them. So, and so here, the joint relative frequency, and I keep using this vocabulary just so we'll all get better at it. 0.291, 0.35, and 0.168. And I'll calculate one of these things here. So we've got, if I divide this out, I get 0.353. This is 0.647. This is 0.634. And this is 0.366. Now, I want to point out 0.353 is different than this one, right? This was a probability that someone was attending given that they were a junior, while, let's see, here we go. This is the probability that someone is a junior given that we already knew they were attending. Okay, and so this was comparing a different thing. And so this would be valuable for someone that was at the event, and then we're trying to figure out, what percent of that population were juniors? 35% of those who were attending were juniors, and 64 were seniors. And so that's the way that that would work. So these are conditional relative frequencies. I'm going to let's see. I think we might be all set with just those ones. Let's jump to this one. So, finding conditional probabilities. So you don't necessarily need to have the table all set up. Sometimes you can kind of answer these questions based on your own analysis. But here we go. So here, a satellite TV provider surveys customers in 3 cities. The survey asks whether they would recommend the TV provider to a friend. Here are the joint relative frequencies shown below. And so, actually, I'm lacking... Hey, quiet, buddy. You're really distracting me, okay? I'm lacking the marginal relative frequencies here. And so that might be worth generating... I guess it depends. But here it would be 0.34. This would be 0.30. These I'd have to add all the way across. Let's see. Well, I'm going to trust a calculator here. Here I'd have 0.88. And 3 is 8 plus 4 is 12. So 0.12. And I forgot to do that one. 0.36. All right. And so it might be helpful to have those marginal things, but you could have done this without them and just calculated those later. I just happen to like having those values there. So here's the question. What is the probability that a randomly selected customer who is located in Glendale, all right, and so that's my reduced set of outcomes, given that they're located in Glendale, that they will recommend. Okay? And so in this scenario, the number of people that are all in Glendale are the 0.34. And I could have actually done this as 0.29 plus 0.05 if I didn't write the marginal relative frequencies on the outside. And notice that's exactly the same as the 0.34. And the numerator would have been this value. So the 0.29. And that is approximately equal to 0.333. So you could say roughly 33% of those in Glendale will recommend to their providers. Okay, and so I reduced the total set of outcomes. I'm doing a conditional probability, right? So this was probability rec given Glen. All right, so that's the way that works. Here's another one. Let's see. What is the probability that a randomly selected customer who will not recommend? And so notice this time, those who don't recommend, I'm looking at this value. And so there's two ways I could have figured that out. If I didn't calculate it there, it would have been the 0.05 plus 0.03 plus 0.04. And so the denominator is just the 0.12. So this is looking at all people who didn't recommend it, right? What's the probability they happen to live in Long Beach? Okay, and so that would be the 0.04. Uh-oh, guys. I think I made a mistake. Yep, I did. I diddly doodly. This isn't 33%. You probably are wondering, and you're correct. I done did that wrong. Here we go. This is the worst way of erasing. Mr. Wouty. I try to be quicker here by having the numbers ready, so you're not listening to me punch buttons on a calculator. Sorry. So 85.3% was here. This one, that's actually this would be the right 33.3%. So of the people who said no, they wouldn't recommend, a third of them lived in Long Beach. Okay, and so notice that you can kind of ask these questions two different ways. Now, this problem gets a little bit more interesting in this question here, and this actually goes back to when we were talking about probabilities of independent events in a last section, I guess, 10.2, I believe it was. Yeah, I think so. Where I'm going to try to figure out, are these two different probabilities similar? And so I'm going to figure out, let me read this question. Determine whether recommending the provider to a friend and living in Long Beach are independent events. So I've got to figure out what's the probability of someone being in Long Beach and I've got to figure out what's the probability of someone living in Long Beach given that they, yes, recommended to their friend. Okay, and so if these two probabilities are the same, then it would seem to suggest that the events are independent. If they are different, then there seems to be some dependence between those. And that would be worth it, trying to figure that out. Like, if there seemed to be a dependence, is you're not being recommended because maybe your service is unreliable in Long Beach specifically, right? Or is there maybe some competition in Long Beach different than the other cities that happens to be offering better service or a lower price or something like that, right? Is there something unique about that scenario? And if there was a dependence, being able to identify that would be valuable. So what's the probability of living in Long Beach? Well, that I can calculate by just adding these two things. That would be the number of people who said yes and the number of people who said no, who lived in Long Beach. And if I add those together, I would get 0.36. And so there's the probability that someone lives in Long Beach. Now, what's the probability that someone lives in Long Beach given that they said yes? Okay. And so all people that said yes were all three of these. Okay. Which is the same as this right here. 0.88. And someone from that group that lived in Long Beach was the 0.32. And if I divide those two things, I get approximately 0.36. That's probably exact. And since both of these are the same, let's see, I guess I'll write it in a different color to try to indicate it here. So because these are the same, therefore they are independent. Okay, and so by considering both of those things, you're trying to figure out whether they're independent. They have the same value, and so they are independent of one another. Let's see. I'm gonna skip those monitoring progress ones. This one's gonna be a little bit longer. I like to take the time to generate multiple tables and then answer the question. So here's example 5. Aha! A jogger wants to burn a certain number of calories. Man, this guy's going to be burning calories just thinking about math this much to optimize jogging routes. But hey, good for him, good for him. Let's see, a jogger wants to burn a certain number of calories during his workout. He maps out 3 possible jogging routes. Before each workout, he randomly selects a route and then determines the number of calories he burns and whether he reaches his goal. The table shows his findings. Which route should he use? Okay, and so let me make a regular joint frequency table. So what's the probability he chose route A and reaches the goal? I'm going to convert these tally marks. So 5, 10, 11. This is 6. This is 11. This one's 12. This one's 4 by the looks of it. And that one's 6. Okay, and let's figure out, we'll fill out the totals. 11 and 6 is 17, 15, 18, 22, 34, 10 and 16. And do these add up to the same thing? That's 40. Yep. All right. So did he go for it? Were we told that in the? No, it didn't say. It just said he chose a different route. Now, one of the potential challenges here is that the routes were disproportionately selected, but data doesn't always come out, that exact way. Randomly doing something doesn't mean it would have been divided evenly. And having done it 40 times, 40 is not divisible. Oh, no. Oh, Waddy. 50. Boom. There you go. 50 is still not divisible by 3, though. So it wouldn't have come out exact anyway. But we'll still be able to do an analysis and figure out how this works. All right. So now that I've got the joint frequencies and marginal frequencies figured out, let's figure out the joint relative frequencies. And so remember, for joint relative frequencies, I'm always doing this out of 50. Okay, for these as my denominator. And this problem is kind of a nice summary of the entire section, and so it's worth doing it. And then I'm going to compare that to what was the joint frequency for that particular column. Right. All right. And so now that if I divide these things out, here I get 0.22. Here we'd get 0.22. That makes sense. And 0.24, and add those up. So what would this represent? 68% of the time he reached his goal of burning the set number of calories he wanted. If you divide that, and these two are the same, so yep. And this one is 0.08. And add these up, and you get 0.32. So 32% of the time he didn't reach his goal. If I add these across, that's 100%. That should be reality. And then when I add these across, I get 0.34, 0.30, and 0.36. Okay, so these black cells here are the joint relative frequencies, and the gray cells are the marginal relative frequencies. And now that I've got this set up, I've got a... Oh, where are my questions? Oh, which... Aha, okay. The table shows his finding. Which route should he choose? Okay, so I've got to be able to analyze this. Let's see. I'm gonna give myself space up here. So I want to figure out, kind of proportionally, which route gives him the greatest likelihood of reaching his goal. All right, and so I want to figure out probability that he reaches goal. I'll just say goal, given he chose route A. I want to figure out that, right? So if he chooses route A, what's the probability that he reached his goal? I want to figure out the probability he reached his goal given that he chose route B, and I want to figure that out, probability he reached his goal given he chose route C. And so let's figure this out. So the probability that he reached his goal and it was route A was the 0.22. Oh, and since all of these are with respect to reaching goal, Oh, no, it's given by route. Okay, so I'm working by rows here. So my denominator here is going to be 0.34. My denominator here would be the 0.30 and 0.36. Because I don't want to just figure out what's the probability he reached his goal. I want it based on which route, given he chose a particular route. Okay, and so this one's going to be 0.22, 0.22, and 0.24, and equals, I guess the division sign is yellow in this case. Ba-da-ba-ba-da. All right, so 0.22 divided by 0.34 means I got 0.647. So that means if he chose route A, he met his goal 64.7% of the time. All right, that's pretty good. It's less than, however, the total number of times he reached his goal. And actually, that's a bit of intuition there as well. Since that particular route is less than the average, you could say, number of times reaching his goal, it's probably not the best, right? Because it's lower than average. Let's see, if I divide this one out, we get 0.733, and so 73.3% of the time, when route B was chosen, the goal was met. And lastly is 0.667. And so whenever he chose route C, he was only successful 66.7% of the time. And so based on this, he should choose route B. All right. Route B resulted in reaching goal more often. Now, personally, I don't like running, but if I was to run, even though this one's like better than the others, I'd rather have variety for my brain rather than like choosing the same route all the time. And I think in the long term, for me personally, I would be more successful because I'd probably be more consistent with running if I gave myself that variety. But I don't know. Anyways, so that problem kind of went through the whole gamut. So here we found the joint frequencies and marginal frequencies. Then we found the joint relative frequencies and marginal relative frequencies. And then these were, I could have made this in the form of a table. These were the marginal, conditional relative frequencies, right? Given a condition that they went a particular route, that they met their goal. And so these were conditional relative frequencies on the basis of rows in this case. I could have argued going the other way as well, but that's answering a slightly different question. All right. Whew, man. Takes a while. A lot of number crunching, a lot of tables. The online version of your homework, though, isn't that bad. You like just drag the numbers into the cell, so it's pretty easy. But thank you. Hopefully you're getting a little bit better with the vocabulary. Have a great day.